plus L2 to L1 minus L2, that's eventually what you will get. So this is the way it actually goes. Now that I know this is the way it goes, now let's see how I can do this. How do I get my resultant? I get my resultant by adding these components. How many possibilities do I have here? 3. How many possibilities do I have here? 3, 2 and 2. So in how many possible ways can I add these up? I can take any one of this, I can take any one of this, any one of this, and any one of this, and then add them up. How many total possibilities am I going to get? 36. Because it's 3 into 3. So 9 ways of putting these two together. There's 2 ways of doing this, 9 into 18 and 36. Essentially, I can put these 4 quantities, L1, L2, or ML1, ML2, MS1, MS2, in 36 different ways and get a resultant. And then pack up all these resultants to see what my vector really is. And that's basically what I'm going to be doing. So you can see, I have raised myself up to write 36 combinations and see what I'm going to get out of it. If I gave you this problem in an exam for a D2, how many possibilities did you get? D is how much? 5. And there are 2 D's, which means there's 25. And the S is going to be, again, 2. So it's 5 into 5 into 2 into 2. 100. And I'm very sure if that's the way I did it, we'll have nobody from here doing chemistry in the 30s. So we won't do it. So the whole point therefore is you really have to work these out. Or if I really want to be very nasty on you, I can do it for the F2 configuration. Write out all the possible states for the F2 and give me the term states for F2. Probably will kill me by it. And that's basic. So we'll do for D2 because, P2, 36 states, and we will see from 36 states how we work it out. Before we do this, let's sort something out. What are the possible states we got for non-equivalent electrons? Triplet D, triplet P, triplet S, singlet D, singlet P, singlet S. What's the degeneracy of this? D is 5 always, right? Because capital L is 2, but capital L is 2 also gives me a degeneracy of 2L plus 1. Therefore, the moment I say D, the total orbital angular momentum L equals 2 will also have a degeneracy of 5, which means the total orbital angular momentum is a big capital L vector, which has a length of root of capital L into capital L plus 1. How many ways can it be oriented? Plus 2, plus 1, 0, minus 1, minus 2. Therefore, it has a degeneracy of 5. This is actually the spin degeneracy. It's 2s plus 1. So what's the degeneracy of this state together? When I say degeneracy, I'm simply saying possible levels it can have within itself. The P is triply degenerate, right? Px, Py, Pz. So likewise, triplet D, what is the total degeneracy of that going to be? 15, right? It's 5 here and 3 here. So totally there's going to be 15 possible. How much is this going to be? This is 3 and 3. 3. Because this is 1. S equal to 0, the degeneracy is 2s plus 1 or 2l plus 1. So it's going to be 1. How much is this going to be? 5, 3, 1. Add all these up. 5, 8, 9 and 9, 18, 21, 36. So which means all these fellows, basically the 36 possibilities that I have actually added themselves up in such a way that I get these states, and these states together give me a total degeneracy of 36. And this is a cross check that you must do all the time. When I give you an electronic configuration and you have eventually come up with states, you must see what the degeneracy here is, that is what that number is, and we saw it is 36. And then you must check the degeneracy of the states that you got and see whether it adds up. If you got 36 there and 45 here, you know you have made a mistake. You have missed something. But this is okay. But what are we now trying to say? We are saying that 36 is not what is going to be allowed for a P2 configuration with the equivalent electrons, because some of these states are not going to be allowed. Pauli principle will simply kick in and tell you, throw some of these states away, you can't have them. And that's basically what we're trying to do. But we're going to be writing all 36 states and then figuring out what happens. The reason I'm going to write it in a certain format is that once you write it in this particular format or in this particular way, you'll start predicting as to what is going to happen later. That's the reason why you will see. You can do it in any way. You take this one, this one, this one, this one, this one, this one. You've got to make combinations. But if you make the combination in a certain planned way, you see that things become that much simpler. And that's basically what I'm going to do. I'm just going to put a number here. This is ML1, ML2, ML2, So let's do it now in this first combination. Number 1. I'll take -1. ML1, I'm going to take -1. And MS1, I'm going to take minus. This I will take -1. This I will take minus. So ML1 is -1. MS1 is -half, ML2 is -1, MS2 is -half. It actually means I'm taking this and this, this and this and forming one combination. What will I get? If I take ML1 and ML2 and add them up, that's actually the X or the component for my capital L, right? So when I add L1 and L2, I should get L. But when I take the ML1 and ML2 and I add them, what am I going to get? I'm going to get the component of L, and therefore I will write it as M sub L. And what is that going to be? -1, which simply has to be -2. And this is a -half and this is a -half. And what does that give? -1. So this is the first combination I have made of the possible 36 combinations. I have taken ML1 to be -1, MS1 to be -half, ML2 is -1, MS2 is -half. And when I add the two components of these, I get the component of ML, and likewise I get the component of MS, and this is basically what I have got. So I have got a component of ML equals -2 and MS equals -1. We are a long way before we can decipher what this means, but we are simply at this point in time writing all the possible combinations and seeing what can happen. Now tell me one thing, is this an acceptable combination? That's how we apply the Pauli principle here. Is this an acceptable combination? No, because L1 is the same in both cases, ML1 is the same in both cases, MS1 is the same in both cases. So essentially this particular orientation or this particular configuration that you have written up actually has N the same, 2, it's a 2p211. N is 2 in both cases. L is the same in both cases because L is 1 for the first electron and L is 1 in the second electron. L also is the same. What about ML? ML is -1, -1. What about MS? -half. You have actually written out a configuration in which all the quantum numbers are essentially the same, and therefore this is not going to be an allowed configuration because this is a Pauli disallowed configuration. Doesn't work. Okay, let me write the next one. I'll keep this the same. I will do one at a time. I'll keep this the same also. I can make this plus. This is what I meant. You go in a systematic way, you will not miss any of these configurations. So I have kept these the same, but here I have changed it. So what is my ML going to be now? -2 are right, but what is my MS going to be? 0. If ML is -2, what does it tell you? It has to be a substate of what configuration? -2, -1, 0, 1 and 2. That has to form part of what? A D state. So I probably have just written out one component of the D state. And what does 0 tell me over there? MS equal to 0 tell me. It must be a singlet. You remember I wrote this singlet D, singlet P, singlet S, triple P, triple D, triple S, and I said that's perfectly okay for a set of non-equivalent electrons. But for equivalent electrons, what did I do? I cancelled the triplet D off and I kept the singlet D. You can already see why the singlet D is surviving. The singlet D is surviving because this is an acceptable state. We will write everything else and see how the one that we threw away were rightfully to be thrown away. Let me write the third state. Minus 1, minus. We keep that the same. I have already exhausted more possibilities here. So what do? I go to the next one, which is 0, and I put the minus factor. So I'm just going to keep this constant, take one of these, work out both. Go to the next one, work out both. So let me write the other one also. Minus 1, minus 0, and plus. These two 1, these two 1. What is this going to be? ML going to be in this case. Minus 1. And what is this ML going to be? Minus 1. And what is this going to be? Minus 1, because this is minus half and this is minus half. And what is this going to be? So I'm basically just producing all my M capital L subcomponents and capital M capital S components. And then we're going to put all these together and then see how we can get the states that we got earlier. Minus 1, minus, what should I do next? Plus 1, minus. The sixth fellow is minus 1, minus, plus 1, plus. How is this going to be? Minus 1 and plus 1. That has to be a 0. And what is this? Also 0. And what happens here? Minus 1, and this has to be 0. I have basically finished a set of 6 for this fellow out here. Let me write. I think I used too much space here, I should have done. Okay, now let me write the next one. What should I do? I'll keep this constant. I finish all the plus minuses. Now let me say plus. And keeping this minus and plus for 6, I'm going to do all these possibilities over here. Okay, so what does that mean? Minus 1, a minus, 8 will be minus 1 plus, 9 will be minus 1 plus, 10 will be minus 1 plus, and 11 will be minus 1 plus, 10 will be minus 1. And just run through this minus 1, 0, 0, 1, 1. And here is minus plus, minus plus, minus. So basically I have just changed one of these and I'm running through all the other 6 combinations to see what I should get. Now let's see what happens here. Minus 1 and minus 1 is going to give me minus 2 and this is going to give me 0. Let's take the next one. What is this? Minus 1, minus 1. Both are same. The plus and the plus, both are same. L1 is same, N is same. So what happens to this particular configuration that you has to be out because it's a Pauli exclusion disallowed state. Therefore, this fellow, even though it would have given me a minus 2 and minus 1, is out because it is Pauli disallowed straight. But what about the first configuration? Look at the first configuration and compare that with configuration 2 that you wrote. What's the big difference between these two? Compare this configuration that you wrote, 7, with configuration 2 that you have written. It is minus plus, this is minus plus. This is minus 1 minus, minus 1 minus. So what have we actually done? The same thing, you switch the labels. But then if you go back and look at the Pauli exclusion principle, and you look at these rules, what do they say? Electrons are indistinguishable particles. You can't put labels on these two electrons and say, oh, I can tell you that this electron is minus 1 plus and this electron is minus 1 0 or vice versa. No. If what you have written is exactly the same thing as what you wrote earlier, excepting for a switch in the labels, then that's again a Pauli disallowed state because electrons are distinguishable. You can't put labels and say that I can figure out this configuration as being different from this configuration. Not possible. These therefore will again become Pauli disallowed states. Because if we go back and look at the Pauli exclusion principle in its entirety, it will simply say, for a set of indistinguishable particles, that's how it will start. A set of indistinguishable particles with half-integral spins, electrons half-integral spins. Of course, it will say something much more. It will say that the total wave function must be antisymmetric for the exchange of these two particles. In simple terms, what it means is no two electrons can have all the four quantum numbers the same. That's a very watered down version. But the more profound statement of the Pauli exclusion principle is the one I just stated. Don't be scared by it. When you do quantum mechanics, you will see what that really means, what a total wave function is, and so on and so forth. But the operative parts are two things. One, if you switch the two particles, the wave function must be antisymmetric, which means that if I had everything the same and I switched them, nothing would happen. That's the reason why we don't allow these states. We don't allow these states because they are exactly the same, and if you switch the two electrons in the sky, you would get exactly the same wave function. They would not be antisymmetric. What do you mean by antisymmetric? Where particle A and particle B, and I switch the coordinates, my wave function should become psi should go to minus psi. That's what it really means. That will not happen if all the quantum numbers were the same. And more importantly, the whole thing starts off by saying that electrons are indistinguishable particles, and therefore you really can't put labels on them and say that it is possible for me to distinguish two electrons with their quantum numbers labeled on them. No. If I have already chosen one, I can't choose the other because that would be over.